Okay, we start our morning session with Monica, second talk on Hecke.
All right, thanks everybody for coming back. Good morning. So, all right. So I left off sort of just barely saying what the finite Hecke algebra was. Type A. So I often put a little superscript finite there to distinguish it from the affine or the double affine. And so I'm working over a field F that I haven't told you much about. Almost always I want it to be characteristic 0. I like the not characteristic 0 stuff is beautiful, but for what I'm doing, for here we want characteristic 0. I'm going to take some integral parameter t, right? And then we've had generators that I was calling t1 up to tn minus 1, and they satisfy the braided relations. So in particular, and there's and quadratic relations, right? And so since they satisfy the braided relations, it's going to be a quotient of, well, not the braid group, but oh yeah. Well, you want to really take the group algebra, the braid group. You want coefficients in there for the next algebra, right? So so that's great. So just different quotients in the symmetric group. And my quadratic relation, I wrote it as something factored last time. I'm going to write it, my quadratic relation, in a different way today. I'm going to write it as ti minus ti inverse is little t minus little t inverse. Okay? And that should remind you of, oops, I have to get my crossing right. Wait, nope. Yes, okay. Sorry, my positive and negative crossing it's not, I always have to check. So we've seen relations like this come up in Tina's talk, in Gregor's talk, when we're talking about not-in-link invariance. So we're saying an overcrossing, a positive crossing minus a negative crossing is t minus t inverse. No crossing, smoothing. And you'll see in the literature, we saw it in today's talk yesterday, that your quadratic relation, when you write it as ti minus some number times ti minus some other number equals 0, you see lots of presentations where you have slightly different parameters in there, slightly different normalizations. You might have t to the 1/2 and t to the minus 1/2. It might be a q and a 1. It might be a minus q and a plus 1. So it really doesn't matter. As long as they're invertible, or as long as they're non-zero, you basically get the same algebra by rescaling the generators, or just like or shifting the generators around. So it doesn't really matter. But it doesn't matter in terms of getting the algebra. Of course, these generators, we maybe want them to have some nice properties, so this is what we take. All right. So from this, of course, you can write out what ti squared looks like. You can write out what ti inverse looks like, so on and so forth. I will leave that as an exercise for you to do on your own. Another nice upshot is this has a basis I can call TW, for W in the symmetric group. That is defined by, again, if W is a reduced expression, meaning you write it in terms of our generator in a minimal way, then we can set TW to be T sub I1, T sub I2, up to T sub IL. And that's well defined. No matter any two reduced expressions for W will give you the same TW because they satisfy the braid relations. That's how the symmetric group works. I have a little interlude here that I was debating skipping, but actually I think, especially because Arun is here, I feel like I have to do this. Okay. So where might Hecke algebras come from? Right? You could just say, oh, I take the symmetric group and I do this deformation, right? So if this is the basis, it has size n factorial, the same as the size of Sn. And again, this is a more general phenomenon that you can do with other Coxeter groups, Weyl groups, and so on. So you might say, well, is that where it came from? Someone's like, let me just tweak the symmetric group a little bit. And no, these occur in nature. So let me say sort of one place that occurs in nature, and which motivates why some people started studying them. We can take G to be GLN FQ. So I was saying, if I took plain old F character 0, I want FQ, finite field. So Q is some prime power, P to the R, where P is a prime. Right? And we can let B be a Borel, which I'm going to take to be upper triangular matrices. And I'm going to let, I feel like I should put bar over my W to just distinguish it from other times I used capital W before, to be the set of permutation matrices inside of here. So we have this nice group-like decomposition. If you want to write double cosets of G with respect to B, these permutation matrices are a very nice choice of double coset representatives. And right, so that means, right, my set of double cosets is in bijection with permutations. And there's an algebra structure that we can put on this. Put some coefficients in there. C, I want to work over C, let's say. So either you can think of this as B bi-invariant functions on G into the complexes with a convolution product. Or the way I like to actually think about it is I like to think of it as a subset, not quite a subalgebra, so it wouldn't be unitable, inside the group algebra of G that basically looks like sums of things like so. And it makes sense, you can multiply these together and decompose them into sums of double cosets. So that's how I like to think about them. More naively maybe because, I first learned about these when I was learning about finite groups when I was an undergrad, and I like groups better than functions. I don't know. I don't like functions that much. So, right. So for n equals 2, for instance, what are we saying? We're saying that GL2 FQ is the disjoint union of upper triangular matrices and one other double coset. That's this 2 by 2 transposition matrix. And let me say what this other double coset looks like. So you might remember double cosets come in different sizes from each other, but you can always decompose a double coset into union of left cosets. I'm going to write it this way. Right, so you can take, this unipotent guy 1A01 by S, A ranges over FQ. This is how to write this double coset as a union of single coset. And that basically tells you the size of this double coset. And using this, you can actually figure out what the product structure looks like on here, either the convolution product, or if you want to write things out naively as inside the group algebra. And let me just sort of say, in general, leave it as sort of an exercise for you to do for general N. So if you have BWB, you can write it as a union over constants in FQ, sort of B SI1, call this like XI2 stick these matrices in here where what is this matrix, right? So this matrix is, well, I'll write it this way. It's the identity plus your AI times E. Well, let me just drop the subscript there for a general I, right? It's it looks like the identity matrix with AI in a single place just off the diagonal. So, for instance, this is x1. Okay? So I think I learned this from Maroon. That was why I had something put it in here. And so this basically tells you that this double coset, if you decompose it into single cosets, how many single cosets does it take? It depends on the length of W. It grows with the length of W. Okay, scaled by Q. Okay, and so exercise for you to verify this, and exercise for you to then basically check that so this double coset, what's going on there? This double coset algebra, we have a couple different ways that we can think about it, which, so you can think of it as, so I said here, you can think of it sitting inside of the group algebra of G, where it's sort of as this corner ring where E is the idempotent, that is basically the trivial idempotent from your Borel subgroup. Okay. Or again, you could say, aha, double cosets, that's about restrict induce versus induce restrict. And or if you think about using the fact that induction and restriction are adjoint to each other, you can see that if you were to induce the trivial representation from B to G and look at endomorphisms of it, this is endomorphism algebra. So again, I don't like the convolution product so much, whereas in endomorphism algebra, it's clear what the algebra structure should be. And again, remember what this was. This was G mod B. Right, this is functions on G mod B, or the permutation representation on G mod B. And so that explains why these three are all isomorphic to each other. But then the punchline is that actually, right, it's your finite Hecke algebra. But of course, there's a Q sitting inside of there. And for the way that I put in like the T and the T inverse and so on there, I want to basically think about my T should be Q to the 1/2 for how I have things written there, or in other words, T squared is Q. But Q is the Q of FQ of the finite field, and it comes up again because of how these double cosets expand into single cosets that you have, right? Q many over here. And then you see that I said sort of length matters in the Hecke algebra in a way it doesn't in the symmetric group, right? So for instance, so we saw in Jose's talk these positions, his capital F, which is all the swaps, ij. And I plus 1 has length 1, but ij has much bigger length. And the symmetric group can't tell the difference too much between those because they're all conjugate to each other. But the Hecke algebra can tell the difference between them, and you sort of see it somewhat in this presentation. Okay, so...
Excuse me, Mike, is this supposed to be clear what the map is, or the isomorphism?
Oh.
HN, or is this not clear?
TSI is basically, let me say it this way, if you're thinking in terms of functions, it would be the bump function on the double coset with coset represented as SI. Sorry, rescaled by Q. You have to rescale it to fit the relations and so on. Yeah.
Formula like that is that true for not just for simple functions, but for all.
And then for all this, you got yeah. So I should have put it up, but then okay. So I'm going to say some constant times T sub w. And again, when you say a bump function, you could instead fold the constant into the bump function by what value is it taking on there. It's good to sort of normalize it to the size of b. It's a bump function on the double coset. Right, so it's clear that functions on these double cosets, a nice basis of them are the things that's 1 on a single double coset and 0 everywhere else. Okay, and that's like your TW basis. And of course, there are more interesting representation theoretic bases for them that I won't go into. Yeah? Good question. Yeah, so I'll leave it as an exercise to you to check the quadratic relation. And I claim it's enough to just do it for n equals 2 to believe it everywhere. So, nice exercise. Check the quadratic. All right, so finally, right, we got to our finite Hecke algebra. Let's pass to affine. So, leave that there so I can use that again in a second. Oh, sorry. Extended. Let's go to my extended affine Hecke algebra. Again, I'm just working in type A. Okay. So we have about 3 different approaches that we've talked about that we can work with, which is, right, I had these pictures. So, okay. Right, we have these pictures for our TIs. When we went for the symmetric group, to the affine symmetric group, what do? We put it on a cylinder. So just put these on a cylinder. Okay? So put on a cylinder. And so, right, so what are we going to do? We're going to have our TIs. And remember, for the symmetric group, what did we add in? An S0. That said, aha, I can just do the same thing, kind of going around the back of the cylinder. So 1, 2, 3, da da da, and here's n. Right, so that's going to be my T0, and it's clearly conjugate to the other TIs, and it's going to satisfy. Oops. I just said they satisfy the braid relations, and didn't actually check. But if you draw it out, keeping the overs and unders the way they are, you can see that it satisfies the braid relation. Okay to leave that as an exercise, drawing that out. So, good exercise to do on your own. And then, we have pi as well. Okay? And so this is where I realized I had to be careful about, am I thinking about my arrows, drawing them up or down? Because if pi is sort of shifting I to I plus 1 and so on, I think I decided, for the sake of how I was doing things, my arrows were kind of going down. So n is going to come back around and go to 1 here. So that's going to be my pi. Okay. So that's a very natural way to get our extended affine Hecke algebra. And the relations, other than the quadratic relation, they actually look exactly the same for the affine symmetric group. And it's quite clear that pi is going to conjugate, right, a ti to a ti plus 1. And we'll have infinite order. I should say, I used the word diagram automorphism last lecture, and I shouldn't have. There was this confusion about, oh wait, does that mean that you're taking pi to the n to be trivial? You're poaching out by that relation. And I'm not. And if I said diagram automorphism, it could make you think that it is, but that's because I was thinking in like SL versus GL land. So forget I said diagram automorphism. Just think of pi as pi. Okay. So we have it this way. We also have generators and relations. Well, now if I write down generators and relations, they should be, you know, completely believable. So 1, we could put it on the cylinder. 2, we can do generators and relations. Well, so we've got t1, tn minus 1, t0, and pi. And we have the braid relations. And we still have the same old quadratic relations. T minus T inverse is T minus T inverse. And then for pi, I just write my new pi relation. So pi, Ti, pi inverse is Ti plus 1. So, easy. Okay. But now remember, before I get to the sort of third way, I had these elements, these x's, that wrapped around the cylinder once and came back. And now it's not totally clear what the x's should be. And so you draw some pictures and you get it wrong a few times and you're like, it's this thing or this other thing, and you know, which one is it? And yes.
First, I like to call it affine Hecke GLM, so I don't get confused.
Sure. Yeah,
But
no, type A.
Is it obvious that pi to the n is central?
Oh, is it obvious?
Is it a consequence and is it obvious?
So the thing is, I am so bad at topology that if it was obvious from just drawing the picture that the full twist was central, I wouldn't be able to see it. I remember Tina even mentioned this yesterday, right? Pi to the n is that full, right? 1 comes back to 1.
Oh, because T0 goes back to T0.
Oh, yeah, from that, yeah. Thank you. Sure, let's make an observation. Is there another question somewhere? Okay. So these x's, these xi's, I'm going to write them as capital Xi's. Right, so they already live in the algebra, but if I want to single them out, what would be the picture for it? And I'm gonna unroll my cylinder because my drawing skills work better like that. So an xi, right? So what did I want to do? I wanted to wrap around the cylinder once in an increasing manner and come back, right? So if I just said, so don't write this in your notes yet, right? So in the symmetric group, this is what it was doing. But I have to tell you with this over and under crossings what's happening. And so my rule of thumb that helps me do this correctly is that, and Eric Rains taught me this, sort of. I mean, I was supposed to be teaching him things about the Hecke algebra, and he was like, he was so quick. He was like, oh, this is just happening. I was like, I didn't mean to say that, but you're right. So, you know, you have 1 and 2 and so on, down to n. You kind of decide very arbitrarily, not canonically, but to make things work, that the 1 strand is always above the 2 strand, is always above the 3 strand, and so on. Okay, so if I were to rewrite this, I would say, I'm going to draw my 1 strand, I'm going to draw my 2 strand, I'm going to draw my 3 strand. Eventually I draw my I strand. Oh, well, right, it's underneath everything that came. And now I draw my I plus 1 strand, and so on and so forth. And if you do that, things will work out correctly. Okay? And
But what do you want to work out correctly?
oh yes,
It's just a definition.
that's a good question. Yes, sorry. So we have an alternate presentation, Bernstein presentation. Which is you have the t1 through tn minus 1, and then x1, x2, and their inverses, up to xn minus 1. Okay. Modulo relations. And what are the relations? These guys form a Laurent polynomial subalgebra. And I'm going to write up there in case you can't see that well. So we want kind of the braid groupy analog of the relations we had before for the symmetric group.
So there's no 0 anymore. Is that right?
There's no 0 anymore and there's no pi. There's no 0 and there's no pi. So when we had the affine symmetric group, we also had two different presentations. We could take the 0 and the pi and take everything like that, or we could have taken the thing that was just like the finite symmetric group, or like the finite Hecke algebra.
I mean, even in the picture, there's no 0.
In the picture, there's no 0. You treat n like 0.
Oh, n is 0. I'm
N
sorry.
is like 0.
I'm
You do
sorry.
everything
N is
modded.
0.
N periodic. Yeah, remember, sorry. Right, these
Sorry,
pictures
sorry.
are n
I
periodic.
take it back. I take it back.
Good reminder. So, what are these relations? With this normalization of the t's, it's that ti, xi, ti is xi plus 1. Okay, and that's what happened with the symmetric group. You wanted to, well, okay. With the symmetric group, we were conjugating. We had like maybe an si, xi, si inverse. And so whether you're taking s's or t's or t inverses matters. In the Hecke algebra, it doesn't matter as a symmetric group. But this, for this to be my chosen relation for the x's, this is the way you can draw it with my choice of over and under crossings and etc. that will work. And if I had chose the negative crossings or did something slightly different, and you look at ti, xi, ti, it'll just become a big tangled mess. And so from this, you can figure out what ti does with xi plus 1, and ti will commute with an xk. Whoops. K is not I or I plus 1. So I didn't write down the relation explicitly with I plus 1, but you can get it from this. So that's an alternate presentation. And this is the presentation I grew up with, which for certain things you want to do is great, and not as great for certain other things. So,
So does the quadratic relation for T0 translate to something else in this presentation?
the quadratic relation for T0 is the same as the quadratic relation for all of the other T's.
Yeah, but in this presentation you don't have T0.
Oh, yeah.
Does it give rise to a new relation?
No, let me just tell you how to go back and forth between the presentations. Maybe that will answer it. It's fine in my notes. Yeah, so how do you go back and forth between the two presentations? Well, I think we said, oh, maybe we did at the end of lecture, how to go with the symmetric group, even back and forth, right? So how do you go back and forth? This is enough to do it. Pi is x1, t1, t2 to tn minus 1. So once you write this down, and you can draw it for yourself and check, that will tell you how to see pi inside of here. Once you have pi, you can get t0. Because if you conjugate t1 by pi inverse, it'll take you to pi 0. t0, take you to t0. Or if you conjugate tn minus 1 by pi, it'll take you to t0. So you can find t0 inside of here. Okay? Likewise, it tells you how to find x1 inside of here. And then you can use this relation to figure out what x2 and x3 and so on look like. And you can really draw it out and check. And again, and then, right, note, it will still be true that pi to the n is the product of all the x's, which will be the full twist, which will be central.
So sorry, there's something basic I realize I'm not understanding.
Sure.
So when you write ti inverse up there, is that inverse the same as the xi inverse that you're writing down below? You see what I'm saying?
Ti inverse should not be the same as an xi inverse. No, x's and t's are very different from each other.
No, I don't mean same elements. Is it the same meaning of inverse?
Yeah, same meaning of inverse.
Because down below you're explicitly adjoining these inverses to your set of generators.
So, yeah, so like you get for free that x is invertible because all of these guys are invertible.
Ah, so you didn't need to write. I see. Okay.
I mean, I guess I should have, okay, so maybe I should have put in a relation. Maybe I should have said pi and pi inverse. Maybe I explicitly should have said pi is invertible and thrown it in there.
And so in there, one of the relations, because of the way you've written the generators, one of the relations is x1 times x1 inverse is the identity.
Yes. Yes, okay, I was floppy about that. Yes. X1 inverse is the inverse of X1.
And can you say again what?
Yeah, when I said that this was a Laurent polynomial subalgebra, maybe that was my cheaty way of saying that. Yeah.
Give me the T inverse.
If you multiply
The invertibility of T is implied by the Hecke relation.
Yeah. As long as little t is a unit, big T will be invertible. Because it's big T plus little t inverse minus little t times the identity.
Is what David called the Hecke relation what I should be considering as the braid relation?
No, the Hecke relation.
The quadratic relation. The quadratic relation implies that big T is invertible. Because we take our parameter to be invertible.
Thank you very much.
And the representation theory is very different, say at T equals 0, and I don't study that, but some people do.
So did you say that the xi commute?
Yes. Well, okay. Yes. I said they form a big Laurent polynomial subalgebra, which in particular means, yes, they commute with each other. I should have. Sorry. That's what poly is supposed to do. Sorry. Two terms. Yes, they all commute with each other. X1 inverse is the inverse of X1, and so on. So let me speak a second about the word affine. So one reason that it's the affine Hecke algebra, just like it's the affine symmetric group, is we've thrown in this affine reflection, T naught, right? When we draw that hyperplane, it wasn't through the origin. Another way that you can think of it as being affine is we took the finite, we extended by this polynomial or Laurent polynomial subalgebra, and that's think like affine space, throwing in polynomials. It's another way to think of it as affine.
Sorry, so am I supposed to think of this, so let's say that lowercase t is plus or minus 1, and am I think of...
Then you'll get the symmetric group.
Great, so that's what makes the capital Pi's behave like reflectors somehow. So I should think of this as deforming that somehow for lowercase c naught plus or minus 1.
Correct. Thank you. Correct. And as someone came up in Jose's talk, we also the representation theory is going to be vastly different whether T is a root of unity or not. But since I haven't quite gotten to the representation theory yet, for the moment we could allow that. So I mentioned we had a couple different ways of getting to the affine. So pictures, generators, and relations. What's the other way? It's like G mod B stuff, right? This way that the finite Hecke algebra occurred in nature, the affine Hecke algebra also occurs in nature by a similar construction. And I think there's a chance it'll come up in some of the talks next week, so I think it's worth touching on.
Can I ask one more terminology
Absolutely.
question? Does the fact that I have Laurent polynomials the reason for the adjective affine?
The Laurent part isn't, the polynomial part is.
Because when I think of affine, I was told I should think of something loopy, and so that's why when I see Laurent, I think
The word affine originally came from translation. Affine value. Wubaki coined that. So this is really, so this is not contributing towards getting to the DAHA and the representation theory. This is the more, this might come up next week. Motivation for affine Hecke algebras occurring in nature. So I'm going to read, so we can have a field that could be something like the p-adics, or the fraction field of, power series in T. Forget the Laurent series. Laurent series in T. Thanks. Or you could take some other local field. Okay. But these are the two main examples that are fun to think about. You could take a finite extension of QP. O be its ring of integers, so the p-adic integers, or power series in T. Oh, T. Shouldn't use T. Dang it. V.
And then this guy has a unique maximal ideal, right? The maximal is generated by the prime p or by the variable b, right? Remember, right? Anything with non-zero constant term in here is invertible. So this has a unique maximal ideal. And so you can go from O to O mod M, which will be your field, you know, F, P, or C, or whatever it is. Okay. And I'm going to call this guy, in general, I'm just going to call it omega. It should actually be kind of a funky pi, but we're already using pi for something else, and a funky pi kind of looks like an omega to me. Okay, and this is this uniformizer. So uniformizer just means a cyclic generator of your maximal ideal. Okay. And so some things that you can look at are, say, GLN K, or you could put some other algebraic constraint. So you can put GLN K over the big field, which is going to be my G. And inside of there, you could look at things like GLNO, just taking entries from NCP. And inside of here, you can take a subgroup called I, which is an Ewell-Horry subgroup, which I'll define in a moment. You could also take a Borel inside of here if you wanted. And so, can you see if I write down here?
No. Sorry.
No, I would rather have it show up. So, taking my projection O to O mod M, you can just do that inside of matrices. I'm going to call that math psi. It doesn't matter what you call it. So, this is like your GLNFQ, right? Or GLNFP, or GLNC. So it contains your honest Borel, your upper triangular matrices. And your Ewell-Horry subgroup is just a preimage of that. Okay, so what is it going to look like? Right, you're going to have things from your maximal ideal below the diagonal. On the diagonal, you need stuff not in the maximal ideal, meaning units, things that are invertible, and you can have anything from your integers up there. And instead of looking at G mod B on both sides, double cosets, you do this with I, the Ewell-Horry. Okay. And it turns out that, whoops, I want whatever field you want to put the button.
Can you write G, K, yeah.
Sure, I
There's so many G's for
There's so many G's, yes. Yeah. So this is isomorphic to your extended affine Hecke algebra, which I write AHA. Okay, and so let's say, so what's similar to what happened in the finite case?
Should I think of I as a way to extend the flagging from just the origin to something a little bigger than the origin, but in some noble way?
So there is a flaggy, there is in terms of flags a way to think of it, but it's very much tied up with looking at the integers in here and the powers of the maximum ideal, and I'm going to get it wrong if I try to answer off the top of my head if I haven't looked it up carefully. But Arun, in the exact words he uses, the answer yes, or do I have to modify that?
Lines of O lattices.
Thank you, O lattices. Yeah, O lattices.
And it's another choice of uniformizer that allows you to use the word lattice.
Well, O is, I mean, when I say lattice is a free O module. So I'm looking at O modules, and then I look at flags of O modules. And they uniformize.
Thank you. All right, well, I'll say that in a bit. So let me get into specifics. So right? So before we wrote things as a union of double cosets, right? You do the same thing here. You do double cosets, and then you're like, what is the set here? I used a W bar before when it's permutation matrices. Let me make it a W wiggle. So what is that? Those are the correct kind of permutation matrices that you had before. So then, an SI is replaced with, the correct permutation matrix. But the thing is, what are S0 and what are pi going to correspond to for the way that this is going to be? This is going to be isomorphic to the affine symmetric group, right? But in terms of matrices, what am I going to do? Well, right, you'll be the identity for 2 through n minus 1. And then you want to do something that's like swapping 1 and n, but you basically need to put your uniformizer. You sort of swap 1 and n, but you're multiplying by this omega and omega inverse. Just like in the vectors, right? We swapped the position of the a1 and the an, but we added 1 to 1 and we subtracted 1 from the other. That's what your uniformizer is doing in terms of what's happening with O and with having O as a
And then omega inverse or omega minus 1.
omega inverse. Right, so then this will still square to 1. You can check. And you have to just check that it has satisfies the braid relation, but that's 1, that's n minus 1. You just have to check it. Okay. And then pi, what is that going to do? Right, well, pi basically looks like an n cycle, but instead of having, then there you have a uniformizer. Okay. And in general, what does this group look like? It looks like permutation matrices, but instead of having just ones in the non-zero entries, you can have powers of your omega, positive or negative. And then it's pretty clear why that looks like the semi-direct product of the symmetric group and z to the n, because those z's are the powers you can put on your uniformizer.
Omega is your wonky pi.
Omega is my wonky pi, yes. Which is why I could have used a wonky pi, but because of
And what's the parameter t?
Oh, for the quadratic, you mean, so you're asking when you do the quadratic relation what actually falls out. I didn't go through and check and write it out. It will be the order. Well, not as the way that I normalize it. Like, so right when I had so if I had used the quadratic relation instead of, if I had said like t minus q times t plus 1 is 0, that q would become, yes, the order of the residues as well.
Yeah, Q is P inverse.
Thank you.
So what if you're working on the
Oh, when you have complexes, and then you have.
Then you have to know what the order of C is.
You have to put some measure on something and then say, so you could think of the Q, one way to think of, you could think of Q as the size of FQ, but you could think of Q as BSB, how many single cosets did it decompose into? Right, that was also Q. And now, of course, well, it's a dimension thing, it's not a raw number. So you want to kind of replace numbers with, good question, I haven't actually gone through and checked. You make a choice somewhere about some kind of measure you're putting on something to do with it, and then work it out. Okay. Right. So, and then the word flag came up. Yes. Another reason why it's great to see it in this setting is that, when you have something like G mod B, whether your G is GLNFQ, GLNC, or, G of K, we know that, right, G mod B are flags. And so as was mentioned, G mod I will be a flag of O lattices. And so, but flags and these double cosets and so on, for people who study this for GLNC, when you look at a double coset, or you look at something like BWB, that's basically a Schubert cell, right? and its closure is a Schubert variety. So these are all connected to each other. So, okay, I mean, right? So I mean, this is the like the finite field analog of Schubert's law. And then just because I feel like I should say it, is that if you had taken so I had this Hori there, it wasn't a Borel, but another interesting subgroup is, right, you could take GLN of O, and then you could say, let's look at GK mod G. That's your affine Grassmannian, which I'm not going to talk about at all, but it's a good opportunity to say the word when we have all these definitions and stuff up here. Exercise, write out what the xi's look like in terms of making good exercise. Right, and I guess another exercise is if we took double cosets for G of O with respect to G of K, relate that to your affine Hecke algebra. What's the relationship there? Another exercise. So,
Sorry, I just want to understand the terminology. When you say flag of O lattices, are you taking GK mod I?
yes. Right. So the way you think of G mod B as flags is, you take your favorite flag. E1 contains the span of E1 and E2 contains the span of E1, E2, and E3, and so on. And you let G act, and you say, oh, B is the stabilizer of that, and the orbit of it is everything, and therefore, that flag is the same as G mod B. So you want to run through the same exercise here, and so. You want to realize your I, right? If your Borel is a stabilizer of the flag here, you can see why when you pull this back, this is going to be the same.
So now the term O lattice is supposed to connote this like nilpotent family of flags.
Nilpotent. Oh, in the sense like you have like some operator acting on it that kicks you up around and you move back around. Are you thinking about affine Springer fiber?
No, I think I'm just thinking of.
It's like G inside of C.
Yeah.
Oh, inside of K.
Lattice is something that when you tensor with K, you get everything.
Yeah.
So but you see, if you have like higher powers of the uniformizer, then you can have something smaller that's still a lattice.
Yeah.
So you can have a sequence of those things.
Yeah, maybe I'm doing something stupid and I'm thinking of it as being filtered by, say, powers of P or by powers of V in the notation. That's what I mean by the word nilpotent.
That's right.
It's not actually nilpotent, it just goes for everything. Yes, it's right.
Okay. So something else that I should have said maybe back when we were still talking about the finite Hecke algebra is this is not on the way to the DAHA, but still it's worth noting is Macdonald theory. So, right, we have our basis that we know and love for the finite Hecke algebra, these T sub W's. Well, there's some other basis that you could take called the Macdonald basis. And, you define it by, let me call them CWs. you have some involution called the bar involution that takes your parameter to its inverse and basically takes t. So those double inverses there will cancel out and make it, instead of being an anti-involution, an involution. Okay, but it's really just saying ti is going to ti inverse and then extend. And it has some triangularity with respect to the t's, and so let me just say CW sum TU's less or equal to W. Okay, and this triangularity property, the coefficients, you put some restrictions on them as being polynomials in your parameter, and they are Cauchy-Listic polynomials. Maybe with a total factor out front. So anyway, it's this other basis that you define really by saying, okay, they're bar invariant. They have this triangularity property with this known basis, and you do a little bit of work to show that they exist. And so, okay, well, what's the big deal about this Cauchy-Listic basis? Well, they measure things that come from geometry. I had mentioned something about Schubert cells, Schubert varieties, in the second cohomology, there's Poincare duality, there's all of this geometry that I don't study, but that, Cauchy-Listic polynomials measure and tell you lots and lots of very interesting things about. So that's one interesting reason to study Hecke algebras. And these Sergal bimodules that came up in Tina's talk, right, they categorify the finite Hecke algebra.
Can you write little t bar as t inverse?
Sure.
You don't want it to be an involution, particularly for the categorification. No, little.
Oh, little t, thanks. Sure. Sorry, antilinear. So, these indecomposable Sergal bimodules, they don't correspond to this basis, they correspond to the Cauchy-Listic basis. And that's part of what makes them complicated and deep and rich and interesting. And also in terms of, when you do categorification, you have certain positivity, integrality properties that are just kind of forced by the fact that what you're looking at is the shadow of something geometric or algebraic, or higher, and so you're going to get things like integrality and positivity, and so these are like canonical bases, these Cauchy-Listic bases, they have that going on for them, and so these were the right things to go out and look for and categorify.
But the TW also presents as complexes, right? Not too complicated. At least the TI.
The TIs, but but the indecomposable Sergal bimodules, those go.
Yeah, I will talk about it today.
Great, Constantine will talk about it. Yay. Okay. So anyway, there's lots and lots that you can do with Hecke algebras and Cauchy-Listic theory. And in the 5 minutes.
Maybe one question?
Yes.
Suppose I pick t is 1 now.
Yes.
Then it seems the bar involution becomes trivial. Is that right?
Oh, yeah. What you really want to do, you don't want to do that. When you're looking at the symmetric group and you want to extract anything from Cauchy-Listic theory for it, you want to do everything sort of with t-generic, write everything down, and then only afterwards.
Right, send stuff to them.
Yeah, and you don't want to just kind of specialize. You want to take a good limit that t goes to 1 if you're going to do that. So I think since we only have 5 minutes left, what I should do is just go to the definition of the DAHA, and then next time I'll come back and start talking about the representation theory of these different algebras and how to think about them. I'm just going to start over here. So my double affine Hecke algebra, F is some field of characteristic 0. It doesn't have to be characteristic 0, I'm just doing that to make life easy, actually. And now I don't just have t, I have q and t. Okay. Actually, yeah, f can be whatever characteristic it wants. It doesn't need it for this definition. And then I'm going to either say DAHA, I'll use a bold h. And a q and t, I might drop my q and t. And so what is it? So, well, again, I'm going to give you two presentations, and maybe there's even a third way of getting there from using braid groups. So presentation one is that nice, easy presentation, which is, okay, we have our t1, t2, tn minus 1, our t0, and our pi. So we have our first presentation of our affine Hecke algebra in there. And now I throw in a Laurent polynomial subalgebra that I'm calling y's instead of x's. Right, and similar to before, I'll just say Laurent polynomial subalgebra to give you the idea of the relations there. Okay, and then what are my new relations? And again, sorry, this is DAHA. This is sort of my GLN DAHA. And so it came up, I can't remember which talk yesterday, that there's, or if you think about Jose's talk, right, he had sort of, H and H dual. And so, you have these two vector spaces. And here we have a choice of sort of two vector spaces, two lattices as well. And life is just easy if we stay with GL. In other words, having Laurent polynomial here, not some weird subequotient or something a little smaller, etc. Okay. There's other DAHAs around for other types. And you don't just say type A. I guess what I'm trying to say is there's more to this than just saying type A. They're specifying some things with lattices.
So before, should I have thought of a choice of lowercase t or lowercase q as like the value of a function on my uniformizer? Like the uniformizer allows me to speak of like how to evaluate a function on this point called my maximal ideal. Should I think of t or q as having specified the value of a function on that?
I don't think of it that way. Laurent shaking his head, yeah.
Okay.
No. I mean, again, I tend to think of q as measuring how big your double cosets are compared to the trivial double coset. Or, something that kind of measures length. Okay, so what are my relations? Well, I'm going to cheat and say a really compact way. If you take the t1 just to tn minus 1 and those y, that you get an affine Hecke algebra just like if we had y's instead of x's. And some conventions will replace y's and y inverses. I find that annoying, so I'm just going to call this h of y. Okay, so that tells you most of how everything in here new is relating. I can tell you what happens with pi. So pi yi pi inverse is yi plus 1 for I not being n. And actually, you know what? Let I be n. I don't have a y n plus 1. But this is this nice trick, is you think to yourself that you do have a y n plus 1, and you make a q inverse y1. And for instance, that means you don't have a y0. Let y0 be q yn. So this is kind of like when we drew this picture of the cylinder, and Gregor asked, where's 0? And we're like, well, 0 is n. But you care if you get to the 0 by how many times did you wind around the cylinder. Right? If you want to keep track of that winding, maybe that's kind of like the ride we saw in one of the talks, this q can kind of do it for you in the sense that, right, if we label things with all integers, the fact that you identify 0 with n, you don't want to forget that information. You want to stick a q in there. And now if I do that, then that really means that, I could say, pi y0, pi inverse is y1, Oh yes, but you just told me that that's the same as pi qyn pi inverse. And so now that tells me how yn and y1 relate with respect to pi. But I find it much easier to let my subscript imagine that I didn't just have y1 through yn, I have y sub I for I, any integer, and then put in relations like so, that if you add multiples of n, you multiply by various powers of q. So I'm out of time, so next time I will give a second presentation of this. That's the more common presentation, but that's so much harder to work with.
Just a small thing. So there you have a T0 over there, but then you don't have it here. So I'm a bit confused.
Oh, right. So now you say I want to know how T0 interacts with the y's. Well, T0 is just a conjugate of T1 by pi inverse. And so you can work it out from knowing what pi does with y's and what Ti does with y's.
So no further. So T0 is there as well.
So
maybe you should say that there's implicitly there's a relation that the first lines make it an hx or another r.
right, I
You
was
haven't
going to do
written
that
it
next.
on the board, but you
Yeah.
were thinking it.
Yes, that was my second presentation. Yeah, so if you want to know, if you want to know relations between, a T0 and a Y1, I would say, well, that's the same as, pi inverse T1 pi Y1, and then I would just move things around and figure out what I have.
But your DAHA does have relations in it that T1 up to Tn and T0 and pi form an AHA.
Yes.
You haven't written that, so that's the confusion.
Oh, well, no, I had already said that before, right? I'm using, we do know that, so T1 up through Tn minus 1, T0 pi, is another AHA, which later I'm going to show as isomorphic to sort of an h of x. We could put x's in here, right? So there's an AHA sitting inside
And this
here.
is an AHA for little t, I guess, or little.
They
okay.
all have the same quadratic parameter little t. They all have the same quadratic parameter little t.
There are two ahas inside.
And the q is only there.
Yeah, maybe you want to say aha with t as a parameter for both, and then there's the q is an additional.
Mm-hmm. Right. So the DAHA has many ahas in it, but there's sort of two principal ahas that generate it. And this is honestly the most compact way of writing down, though, things that are in there and what all the relations are going to be that are used to remember and to get right. Right, yeah, so remember when I said relations, you have all the old relations you had before. The only new, and I tell you the y's are in Laurent polynomials at algebra, the only new relations I need to give you, right, I see you're right. So I said how pi interacted, I said how these t's interacted. You're right, I cheated and I didn't say how T0 interacted. But again, the reason I didn't need to is that this set of generators is redundant, right? In fact, if I just give you T1 and pi, that's enough to generate all of the t's and pi. So I should have explicitly written out what T0 does with the y, but knowing what finite other ti and a pi does is enough to figure it out. So yeah, I should have included that, but I cheated.
Any other questions? I have one more.
Yeah.
So do I understand correctly that this AHA, this alternate presentation, that gives you a basis?
Yes, we do get a basis of, so you
Just
want to
like
know
for
what
the Hecke algebra, that this is n factorial elements. Now you have n factorial times
the
the
Laurent
Laurent.
polynomials in y.
Is that right?
Yes. So now you have a basis that looks like, say, TW y to the beta, where beta is in z to the n, so these are Laurent polynomials. But my w is now in my affine symmetric group, where by abuse we could say that t sub pi is pi. So give me any reduced word in the affine symmetric group. It's in terms of little si's and s0s and pi. Just turn those into t's instead of s's and keep pi's as pi's. That gives me the affine symmetric group part of the basis, and then you put Laurent polynomials and y's and s, and that's the basis. This is for DAHA. This is the DAHA basis for this presentation.
Now, my question was about the AHA before, and then W would be just the ordinary symmetric.
Oh, yeah, I didn't say that before. So your AHA basis. So the AHA
That's
basis.
what I was hoping.
Yes. So the AHA basis for this AHA is just the TWs for W in the affine symmetric group, where again you take the convention that P sub pi is
Matter
just
of fact,
pi.
he wants to see the other basis where you have TWs
And the
finite
x's?
symmetric group and the x's.
Okay. Yeah. So then that basis. So we have this alternate presentation here with the t's and the x's. So when we have t1 up to tn minus 1 x1. Here the bases are t sub w, x to the beta, w just in the finite symmetric group, and beta z to the n. Yeah. That's the basis there.
And how would you prove something like this? I mean, is this the point about this exercise with the G over I? Like you someone say that that's a bijection?
That wasn't the point. I guess, well, I guess you could use that to show it's a basis. How do you prove it's a basis?
I mean, is there
You have
is
to
that a
do that.
bijection? I mean, is there like before a bijection between these words and the double coset representatives?
Oh, for the DAHA?
No,
Or
for
you
the
mean the
AHA.
AHA?
I'm
The
straight
AHA.
with that.
Sure.
AHA.
Yeah. If you're doing this with the Iwahori, in the same way that the TWs went with the BWB, you would have IWI.
So that would be a way to see
That would be a way to. I think what you do is, how do you prove the basis? I have to think maybe
There are at least 4 different proofs, right? I think you can directly check sine and lemma on the generative relations. You can construct a faithful representation. You can embed it in the symmetric group or the group algebra.
Yeah, I guess the only one I know is producing a faithful representation, which is a big pain, but standard.
Okay, maybe let's have another round of applause.
So